You are listening to Functional Thinking, a beginner's guide to mastering pure functions and modern programming paradigms. Like and subscribe to keep up to date on our latest audiobooks. Functional Thinking, a beginner's guide to mastering pure functions and modern programming paradigms. Chapter 1, The Way of Functions, Why Functional Programming Matters. Imagine you're building with Legos. Each brick is a self-contained unit. You click them together to create larger structures. If you want to change a part of your castle, you simply detach a section and replace it with new bricks, leaving the rest of the castle undisturbed. Now, imagine trying to build that same castle by pouring concrete. If you want to change something, you have to chip away at the old concrete, mix new batches, and hope you don't compromise the entire structure. These two approaches illustrate a fundamental difference in how we can approach building software. Just as there are various construction methods, there are different programming paradigms, philosophies, or styles for organizing and structuring our code. For decades, many programmers have largely operated in the concrete pouring world, building programs where parts are intricately linked and change can ripple unpredictably. But there's another way, a Lego approach, which is increasingly gaining traction in the modern software landscape: functional programming. It's not just a set of tools or a new language. It's a profound shift in how we think about solving problems, offering a path to more reliable, testable, and maintainable software. This book will guide you through this different way of thinking, showing you why it matters and how you can apply its powerful principles, regardless of the programming language you use. What is a programming paradigm? Before diving into functional programming, let's clarify what a programming paradigm actually is. Think of it as a particular school of thought, a set of principles and patterns that dictate how you structure your code to solve problems. It's like having various toolkits, each optimized for different kinds of tasks. You might already be familiar with some: imperative programming. This is the most common, focusing on how to achieve a result by providing a sequence of commands. It's like giving someone a precise step-by-step recipe. First, take 2 eggs, then whisk them. Next, add flour. Object-oriented programming, OOP. This paradigm organizes code around objects, data structures that contain both data, attributes, and methods, behaviors. It models real-world entities and their interactions. Functional programming offers yet another lens through which to view and construct your programs. It's less about giving a sequence of instructions or modeling objects, and more about defining what you want to compute through the application of functions. A brief history of functional programming. Functional programming might feel like a modern trend, but its roots stretch back surprisingly far, long before computers as we know them existed. Its theoretical foundation lies in the lambda calculus, a mathematical system developed by Alonzo Church in the 1930s to explore computation and functions. It was a theoretical framework for describing computation using pure functions, much like a blueprint for thinking about computation itself. The first programming language to widely adopt these functional ideas was Lisp, created by John McCarthy in 1958. Lisp, short for List Processor, was initially developed for artificial intelligence research. It was revolutionary for its time, demonstrating how programs could be built entirely from expressions and functions. Here's an interesting anecdote about Lisp. During the AI winter of the 1980s, when funding and interest in artificial intelligence dwindled, Lisp's popularity also suffered in mainstream computing. Many programmers turned their attention instead to object-oriented programming languages like C++ and Java, which were seen as more practical for building the complex systems of the era. However, Lisp, and with it, the core ideas of functional programming, never truly disappeared. It found strong niches in areas like symbolic computation, rapid prototyping, and specialized AI research. Its resilience proved that its fundamental principles held enduring power, even if they weren't always in the spotlight. The widespread adoption of functional programming languished for decades, partly due to hardware limitations. Early computers struggled with the memory management and performance implications of functional styles. But fast forward to the 21st century, and the computing landscape has changed dramatically. We now live in a world of multi-core processors, cloud computing, and big data. These shifts have inadvertently created an environment where functional programming's strengths truly shine, leading to its powerful resurgence. The why now problems functional programming solves. So, why is functional programming suddenly so relevant again? It's not just a nostalgic revival. It's a direct response to some of the most pressing challenges in modern software development. The concurrency crisis. Perhaps the most significant driving force behind functional programming's comeback is the concurrency crisis. For years, improvements in computer performance came primarily from increasing processor speed. But around the mid-2000s, this trend hit a physical wall. To continue making computers faster, manufacturers started adding more processing cores to each chip. Now, your average laptop has multiple cores, capable of doing many things at once. Writing programs that effectively utilize these multiple cores, that is, writing concurrent or parallel programs, is notoriously difficult. The biggest headache arises from shared mutable state. When multiple parts of your program try to read, and more importantly, change the same piece of data at the same time. This leads to insidious bugs like race conditions, where the outcome of your program depends unpredictably on the exact timing of operations. It's like multiple people trying to update the same single document on a computer simultaneously, without any coordination, leading to a garbled mess. Functional programming, through its emphasis on immutability, data that cannot change, and pure functions that don't produce side effects, offers an elegant solution. If data never changes, and functions don't unexpectedly modify things outside themselves, then multiple parts of your program can safely operate on data concurrently without fear of stepping on each other's toes. Imagine our Lego castle again. If each builder is working with their own copy of a blueprint and then combining their finished sections, there's no conflict in their individual work processes. Functional programming helps us design software in this highly concurrent, independent fashion. Improved testability. Another major benefit of the functional approach is vastly improved testability. In traditional imperative programs, functions often interact with shared variables or external systems, like databases or the internet. This means that to test just one function, you might need to set up a complex environment, ensuring that the shared variables are in the right state or that the external systems respond in a specific way. If a test fails, it can be hard to pinpoint whether the problem is in the function itself or somewhere else in the setup. Pure functions, a cornerstone of functional programming, are remarkably easy to test. Because they always produce the same output for the same input and have no side effects, you simply provide a specific input, check the output, and you're done. There's no need to worry about external state or hidden dependencies. This predictability leads to far more robust testing and ultimately more reliable software. Enhanced maintainability and reliability. Finally, programs built with functional principles tend to be more maintainable and reliable. When you have pure functions and immutable data, it becomes much easier to reason about how your program behaves. You can look at a piece of code and, without needing to inspect the entire history of the program, understand exactly what it does. This reduces the cognitive load on developers, making it easier to fix bugs, add new features, and understand code written by others or by your past self. The declarative nature of functional code also contributes to its clarity. Rather than specifying a tedious series of steps, you declare what you want to achieve, leaving the how to the underlying system. This often results in more concise, expressive, and less error-prone code. Key differences: imperative versus declarative. To grasp the essence of functional programming, it's helpful to understand the distinction between imperative and declarative programming styles. Imperative programming. This is all about how to do something. You instruct the computer step by step on what actions to perform and in what order. It's like giving precise driving directions. Go straight for 2 blocks, then turn left, then go another block, and the house is on your right. Declarative programming. This is about what you want to achieve without specifying the exact steps. You describe the desired outcome. It's like telling a taxi driver your destination. Take me to the Grand Central Station. The driver knows how to get there, but you don't need to give them turn-by-turn instructions. Functional programming leans heavily into the declarative style. Instead of telling the computer how to manipulate data step by step, you define transformations using functions, and the program orchestrates what data gets transformed into what final result. This declarative approach often leads to code that is easier to read, understand, and, as we've seen, maintain and test. What this book will cover. This book is your guide to understanding and applying functional thinking. We'll start with the foundational concepts, then explore how they combine to build powerful and elegant solutions. Chapters 2 and 3 will introduce the bedrock of functional programming: pure functions, immutability, first-class functions, and higher-order functions. These are the most crucial concepts to grasp. Chapters 4 through 8 will delve into building blocks like recursion, managing state and side effects gracefully, various forms of data transformation, like mapping and filtering, functions composition, and intelligent pattern matching. Chapter 9 will demonstrate how functional principles are uniquely suited to tackling the complexities of concurrency and parallelism. Chapters 10 and 11 will give you a taste of functional languages in practice and explore fascinating real-world case studies where functional programming has made a significant impact. Finally, Chapter 12 will look at the broader implications and the future of functional thinking, even beyond strict programming contexts. Conclusion: functional programming isn't just a niche academic pursuit or a passing fad. It's a pragmatic and powerful paradigm that addresses the increasing complexities of modern software development, particularly in a world driven by concurrency and large-scale data processing. By embracing functional thinking, you'll gain a profound understanding of how to build software that is more robust, easier to reason about, and capable of handling the demands of tomorrow's computing challenges. Let's begin our journey into the elegant world of functions. Chapter 2, the core pillars, pure functions and immutability. If functional programming were a towering building, then pure functions and immutability would be its foundation stones. These aren't just obscure terms used by computer scientists. They are the twin principles that underpin everything else we'll discuss. Once you grasp these two concepts, much of the elegance and power of functional programming will begin to click into place. They are the core ideas that equip your software for the complexities of the modern world. Pillar 1, pure functions. Imagine a mathematical function like f(x = x + 1). If you input 5, the output is always 6. If you input 10, the output is always 11. It's utterly predictable. Now, imagine a vending machine. You put in your money and press the button for a sparkling water. You expect to get a sparkling water every single time, and you don't expect the machine to suddenly change the temperature in the room or dim the lights. These are excellent analogies for a pure function in programming. A pure function adheres to two strict rules. Given the same inputs, it will always produce the same output. It produces no side effects. Let's break these down. Predictable output. The first rule, given the same inputs, it will always produce the same output, means a pure function is like a reliable calculator. If you feed it the number 5, it will consistently return 6, never 7, never throwing an error, never producing a different number based on the time of day or how many times you've called the function before. Its behavior is entirely determined by its inputs and nothing else. No side effects. The second rule, it produces no side effects, is crucial. A side effect is essentially anything a function does that isn't directly returning a computed value. Think about our vending machine. If, in addition to dispensing your drink, it also drained your bank account, sent a text message to your grandma, or randomly ordered a pizza, those would be side effects. They are observable changes of state that happen outside the function's clearly defined scope. Common examples of side effects in programming include modifying a global variable, changing data that exists outside the function itself, printing to the console or displaying alerts, interacting with the user interface, writing to a file or a database, changing persistent storage, making network requests, communicating with external servers, modifying the arguments passed into the function, changing an input that another part of the program might be relying on. Why are side effects problematic? While they are often necessary for a program to do anything useful, a program that couldn't print or save data would be quite useless. Uncontrolled or hidden side effects are a major source of bugs and complexity. Imagine you have many parts of your program working simultaneously. If one function secretly changes a piece of data that another function is using, you can end up with unpredictable behavior. Pinpointing which function caused the unexpected change and when becomes a debugging nightmare. This is especially true in concurrent or parallel programming, where multiple operations might be running at the exact same moment. If they all have hidden side effects, you might have a race condition, an unpredictable outcome based purely on the arbitrary timing of operations. Benefits of pure functions. By strictly adhering to the pure rules, functions become remarkably powerful and beneficial. Exceptional testability. Because pure functions are so predictable and isolated, testing them is incredibly simple. You just provide an input and verify the output. No complex setup, no worrying about global state, no mocking databases. This drastically speeds up the testing process and makes fixing bugs far more straightforward. Easier parallelism and concurrency. This is a big one. Since pure functions don't modify shared data and always produce the same output for the same input, you can run many of them at the same time on different processor cores, without them interfering with each other. This makes concurrent programming vastly safer and simpler. Memoization/caching. If a pure function is called with the same inputs multiple times, and you know it will always produce the same output, you can save the result of the first call and return it immediately on subsequent calls without recomputing. This is called memoization and can significantly improve performance in certain scenarios. Readability and predictability. Code built with pure functions is easier to understand. When you look at a pure function, you know exactly what it does just by looking at its inputs and outputs. There are no hidden surprises. Pillar 2, immutability. If pure functions are about predictable transformations, immutability is about predictable data. The concept is simple but profound. Once a piece of data is created, it cannot be changed. If you need a modified version of that data, you don't alter the original. Instead, you create a brand new piece of data that incorporates the changes. Consider a stone tablet versus a whiteboard. A stone tablet, immutable, is carved with information. If you want to change something written on it, you don't erase it. You carve an entirely new tablet with the updated information. The original tablet remains untouched. A whiteboard, mutable, on the other hand, allows you to write, erase, and rewrite directly on its surface. In traditional imperative programming, data is often mutable by default. You create a list of numbers, and then you can go in and change individual numbers within that list. You create an object representing a person, and then you can change their age or address directly within that object. This constant ability to change data in place, while seemingly convenient, is a major source of complexity, especially when working with shared data and concurrency. Think about a bank statement. Your statement from last month, an immutable record, reflects your account balance and transactions at a specific point in time. Future transactions create new entries and are reflected in new statements. They don't retrospectively alter your old statement. This provides a clear, unalterable historical record. Programming with immutable data works in a similar vein. Why immutability? The benefits of embracing immutability are numerous and impactful. Concurrency safety. This is the most compelling reason. If data cannot be changed, then multiple parts of your program, or even multiple computers, can safely read and use the same data concurrently without any risk of one part unexpectedly altering it for another. There are no race conditions over shared data because the data itself is steadfast. Easier debugging. When an error occurs, it's often a nightmare to figure out when and where a particular piece of data was changed, leading to the problem. With immutability, this problem largely disappears. If you have an incorrect value, you know it must have been created incorrectly in the first place or transformed incorrectly. You don't have to trace a long history of modifications. Predictability. Just as with pure functions, immutable data leads to a more predictable system. You always know that a piece of data, once created, will hold its value. This makes your program's behavior much easier to reason about and understand. Simpler sharing. Sharing data references between different parts of a program or between different threads becomes much safer because there's no risk of accidental modification. Putting it together. Pure functions plus immutability. Pure functions and immutability are a dynamic duo. They reinforce each other to create robust, predictable systems. When you combine them, you shift your programming mindset from change X to transform X into a new Y, instead of a function taking a list of numbers and modifying each one in place. A pure function will take the original list and return a brand new list with the transformed numbers, leaving the original list completely untouched. For example, if you have a list of prices and want to calculate the prices after a 10% discount, mutable imperative way, you might iterate through the original list, directly reducing each price by 10%. The original list is now gone, replaced by the discounted one. Immutable functional way. A pure function would take the original list of prices and return a new list containing the discounted prices. The original list of prices remains exactly as it was, providing a clear record and allowing other parts of your program to continue using the original values if needed. This approach might seem counterintuitive at first. You might think, doesn't creating new data all the time waste memory and slow things down? While there are performance considerations, modern functional languages and libraries are highly optimized to make these operations very efficient, often by strategically sharing parts of the underlying data structures. So, the benefits in terms of reliability and clarity often vastly outweigh any minor performance overhead. Conclusion: pure functions and immutability are not just theoretical concepts. They are the bedrock upon which reliable, testable, and maintainable software is built in the functional paradigm. They simplify parallelism, reduce bugs, and increase the predictability of your programs. While it may require a shift in your thinking, adopting these core pillars will empower you to write code that is not only robust, but also a joy to work with. In the next chapter, we'll see how functions themselves can be treated as flexible, powerful components, akin to any other piece of data. Chapter 3. Functions as first-class citizens and higher-order functions. In traditional imperative programming, functions are often seen as commands, a sequence of instructions to be executed. They live in a separate category from regular data like numbers, text, or true-false values. But in functional programming, this distinction largely dissolves. Here, functions are treated with the same respect and flexibility as any other piece of data. This concept is so fundamental to functional programming that it has a special name: functions as first-class citizens. Imagine you have a powerful toy car. You can assign it a name, store it in a variable, give it to a friend to play with, pass it as an argument, or even receive one back as a gift, return it as a value from a function. Functions in functional programming enjoy this same level of freedom and versatility. Functions as first-class citizens. The definition: for functions to be considered first-class citizens in a programming language, they must be able to do all of the following: be assigned to variables. Just like you can say x equals 10 or name Alice, you should be able to assign a function to a variable. This means you can refer to the function by that variable's name. Be passed as arguments to other functions. A function can accept another function as one of its inputs. This enables profound levels of customization and abstraction. Be returned as values from other functions. A function can generate and return a new function as its result. This is incredibly powerful for creating dynamic and flexible code. Be stored in data structures. You should be able to put functions into lists, arrays, or objects, just like any other piece of data. Why is this important? Because it unlocks a completely different way of structuring and composing programs. Instead of fixed, rigid operations, you can now swap in different behaviors, customize actions on the fly, and create incredibly flexible and reusable code. Higher-order functions, HOFS. The power unleashed. The concept of functions as first-class citizens finds its most powerful expression in higher-order functions, or HOFs. A higher-order function is simply a function that either takes one or more functions as arguments, or returns a function as its result, or both. Think of a higher-order function as a function factory or a function orchestrator. It doesn't necessarily perform a direct calculation itself. Instead, it manipulates or uses other functions to achieve its purpose. This might sound abstract, but you've likely encountered the concept in various forms, even in non-functional contexts, through things like event handlers or callback functions. For example, in many user interface systems, when you want something to happen when a button is clicked, you pass a function to the button's onClick property. That onClick property is effectively a higher-order function, waiting for your specific action function to be provided. Let's explore some of the most common and powerful higher-order functions that you'll encounter in virtually every modern programming language, regardless of its primary paradigm. Map, filter, and reduce. These three functions represent fundamental patterns for data transformation. Map, applying a transformation to every item. Imagine you have a list of numbers, say 1, 2, 3. You want to get a new list where each number is doubled, resulting in 2, 4, 6. How map works. Map is a higher-order function that takes two things, your original list or collection and a function. This function, often called the callback or transformer function, specifies how each individual item in the list should be changed. Map then applies this transformer function to every item in the original list, one by one. Crucially, it doesn't modify the original list. It returns a brand new list containing the results of the transformation. Analogy. Think of map as a stamping machine. You have a stack of blank papers, your list, and a specific stamp, your transformer function, say, a doubling stamp. The map machine takes each paper, applies the stamp, and places the newly stamped paper into a new stack. The original stack remains untouched. Audio-friendly description. Let's say you have a lineup of 3 people, and you want to ask each person a question, say, what's your favorite color? You're not changing the people themselves. You're just getting a new list of their answers. The map function does something similar with data. You hand it your list, and you hand it a small helper function that describes what to do with each individual item. The map function goes through your list, applies your helper function to every item, and collects all the results into a brand new list. Filter, selecting items based on a condition. Now imagine you have a list of numbers, 1, 2, 3, 4, 5. You only want to keep the even numbers, resulting in 2, 4. How filter works. Filter is another higher-order function. It also takes your original list and a function. This function, often called the predicate function, acts as a test. It takes a single item from the list and returns true or false. Filter then goes through each item, applies the predicate function, and if the predicate returns true, that item is included in the new list. If it returns false, the item is omitted. Again, the original list is left unchanged. Analogy. Filter is like a sieve or a bouncer at a club. You give it a collection of items, people entering the club, and a rule, your predicate function, only allow people with valid IDs. The filter lets only the items that satisfy the rule pass through into a new collection. Audio-friendly description. Suppose you have a big pile of fruits, some apples, some oranges, some bananas. You decide you only want the apples. The filter function helps you do this. You give it your pile of mixed fruits, and you give it a little helper function that says, is this an apple? The filter function then goes through your pile, asks that question about each fruit, and creates a completely new pile containing only the fruits that passed your is this an apple test. The original pile stays just as it was. Reduce or fold, combining items into a single result. Finally, imagine you have a list of numbers, 1, 2, 3, and you want to calculate their sum, which is 6. Or perhaps you want to join a list of words into a single sentence. How reduce works. Reduce, sometimes called fold in other languages, is slightly more complex but extremely powerful. It takes your list, a function often called the reducer or accumulator function, and an optional initial value. The reducer function takes two things, the accumulated result so far and the current item from the list. It then combines them and returns the new accumulated result. Reduce applies this combining process repeatedly, iterating through the entire list until all items have been processed, and it returns the single final accumulated result. Analogy, reduce is like a blender. You load it up with several ingredients, your list items, and then instruct it on how to combine them, your reducer function, for example, add this to what's already there. The blender processes them all until it produces a single smoothie, your final result. Audio-friendly description. Let's say you have a stack of poker chips, each with a different value. You want to find the total value of all chips. The reduce function can do this. You give it your stack of chips, and you give it a rule for combining. Take the current total and add the value of the next chip. The reduce function starts with an initial total, maybe 0. Then it picks up the first chip, adds its value to the total, then picks up the next chip, adds its value to the new total, and so on. It keeps doing this until all chips are processed, and then it hands you the single, final total value. Closures, remembering their surroundings. Closely related to higher-order functions are closures. A closure is simply a function bundled together with references to its surrounding state, its lexical environment. What this means in practice is that a function, even when passed around or returned from another function, remembers the variables and data that were available to it when it was created. Analogy: imagine you're given a specific instruction manual to build a complex model. But this manual isn't just generic, it's personalized to you. It remembers that your specific model has a red roof, and even if you give this manual to a friend, it still refers to your red roof. The function is the manual, and the variables it remembers are the red roof, specific to its creation context. Closures are extremely useful for creating functions that are custom configured. For example, you might have a function that creates greeting functions. You can pass it a language, e.g., English or Spanish, and it returns a new function specifically for greeting in that language. This new function remembers the language you chose when it was created. Benefits of HOFS and first-class functions. The ability to treat functions as first-class citizens and utilize higher-order functions provides immense benefits. Abstraction and reusability. HOFS allow you to abstract common patterns. Instead of writing separate loops for doubling numbers, filtering evens, and summing lists, you can write generic map, filter, and reduce functions, and then simply provide the specific logic, the transforming, testing, or combining function, as an argument. This leads to less repetitive code and more generic, reusable components. Modularity and flexibility. You can easily swap in different behaviors. Need to sort a list differently. Pass a different comparison function to your sorting HOF. Want to log data in a new format? Replace the logging function you pass to your data processing HOF. Conciseness and expressiveness. Code that leverages HOFS often expresses what is happening at a higher level, rather than how it's happening, leading to more readable and concise solutions. Conclusion: understanding first-class functions and higher-order functions is a pivotal step in embracing functional programming. They move functions from being mere commands to being portable, composable building blocks that can be manipulated and combined in incredibly powerful ways. This flexibility is what allows functional programs to be so declarative, modular, and ultimately, so elegant. In the next chapter, we'll explore another fundamental functional pattern, recursion, and see how it builds upon the principles we've discussed so far. Chapter 4. Recursion. Looping without loops. Imagine you're trying to solve a large, complex puzzle. One way to tackle it is to break it down into smaller, identical versions of the same puzzle, solve those, and then combine their solutions to solve the original. This is the essence of recursion, a method where the solution to a problem depends on solutions to smaller instances of the same problem. In functional programming, recursion often takes the place of traditional loops, offering an elegant way to achieve repetition without relying on mutable state. The loop problem in functional programming. In many imperative programming languages, you're used to seeing for loops or while loops. These loops typically involve a mutable counter variable that changes its value with each iteration, or a mutable state that is updated until a condition is met. For example, a for loop to sum numbers might involve a sum variable that starts at 0 and then gets added to repeatedly, and a counter variable that increments until it reaches the list's end. While effective, this reliance on changing variables directly conflicts with the functional programming principles we discussed, immutability and pure functions. If we're constantly updating a sum variable or incrementing a counter, we're introducing mutable state and side effects into our computations. Functional programming seeks to avoid this, leading us to recursion as an alternative for repetition. Recursion as a functional loop. Recursion allows us to perform repetitive actions or process collections of data without mutating any variables. Instead of changing a counter, A recursive function achieves progress by calling itself with new, smaller versions of its input, moving closer to a known, trivial case. Every recursive function needs two fundamental parts to work correctly. The base case. This is the stopping condition, the simplest version of the problem that can be solved directly without further recursion. Without a base case, your function would call itself infinitely, leading to a crash. It's the point where your function says, "I'm done, I know the answer now." The recursive step. This is where the function calls itself with a modified input. The modification must bring the problem closer to the base case, ensuring that the recursion eventually terminates. It's the part that says, "I don't know the answer directly, but I can get it if you solve a slightly simpler version of the same problem for me." Analogy. The Russian nesting dolls. Imagine you have a Russian nesting doll. You open it, and inside is a slightly smaller doll. You open that one, and inside is an even smaller doll, and so on, until you reach the tiniest doll that cannot be opened further. Getting to the core doll, this is like the recursive step. Each time you open a doll, you're performing the same action on a smaller version of the problem. The tiniest doll, this is the base case. When you reach the smallest doll, you're done. There are no more dolls to open. Example 1. Calculating factorial. Let's illustrate with a classic mathematical example. Factorial. The factorial of a non-negative integer n, denoted n, is the product of all positive integers less than or equal to n. For example, 5 equals 5, 4, 3, 2, 1 equals 120. You can define factorial recursively. N equals n1, the base case is 1, equals 1 or 0, equals 1 depending on definition. How a recursive function for factorial might work. If you want to know the factorial of a number n, base case, if n is 1 or 0, the answer is 1. Recursive step. Otherwise, the answer is n multiplied by the factorial of n1. So if you ask for factorial 5 asks for 5 factorial 4. Factorial 4 asks for 4 factorial 3. Factorial 3 asks for 3 factorial 2. Factorial 2 asks for 2 factorial 1. Factorial 1 hits the base case and says, "The answer for me is 1. Now the answers unwind. Factorial 2 gets 1, calculates 2 1 equals 2. Factorial 3 gets 2, calculates 3 2 equals 6. Factorial 4 gets 6, calculates 4 6 equals 24. Factorial 5 gets 24, calculates 5 24 equals 120. This process clearly shows how a new, smaller problem, n1, is passed to the same function until the base case provides the initial concrete value, which then propagates back up the chain of calls. Example 2, summing a list recursively. Instead of a for loop that iterates and updates a mutable sum variable, we can sum a list using recursion. How a recursive function for summing a list might work. If you want to know the sum of a list of numbers, base case, if the list is empty, the sum is 0, there's nothing to add. Recursive step. Otherwise, the sum is the first number in the list, plus the sum of the rest of the numbers in the list. So, for a list 1 2 3, sumList 1 2 3 asks for 1 plus sumList 2 3. Sumlist 2 3 asks for 2 plus sumlist 3. Sumlist 3 asks for 3 plus sumlist. Sumlist hits the base case and says, "The answer for me is 0. Now the answers unwind. Sumlist 3 gets 0, calculates 3 plus 0 equals 3. Sumlist 2 3 gets 3, calculates 2 plus 3 equals 5. Sumlist 1 2 3 gets 5, calculates 1 plus 5 equals 6. This is a very common pattern in functional programming. Breaking down a collection into its head, the first element, and its tail, the rest of the elements, processing the head, and recursively processing the tail. The challenge: Stack Overflow and tail call optimization. While elegant, recursion has a practical limitation in many programming environments: the call stack. Each time a function is called, a record of its current state, called a stack frame, is added to the call stack. When a recursive function calls itself many times, the stack can grow very deep. If the recursion goes too deep, it can exhaust the available memory on the stack, leading to a stack overflow error. This is a common concern for newcomers to functional programming. However, modern functional languages and compilers often employ a clever optimization called tail call optimization, TCO, or tail call elimination. A tail call is a special kind of function call that occurs as the very last operation within a function's body. If a function is tail recursive, meaning its recursive call is a tail call, a smart compiler can effectively transform the recursion into a simple loop behind the scenes. Instead of adding a new stack frame for each recursive call, it reuses the current stack frame, preventing stack growth and avoiding stack overflow. Not all languages support TCO by default, and not all recursive functions can be optimized in this way. Only tail calls benefit. But for languages like Scheme, Haskell, and others, TCO allows recursion to be a highly performant and safe alternative to traditional loops, even for very large datasets. When to use recursion? Recursion isn't just an alternative to loops. It's often the most natural and clear way to express solutions for problems that are inherently self-referential or deal with self-similar data structures. For example, tree traversal, navigating hierarchical data like file systems, XML JSON structures, or organizational charts. Graph algorithms, finding paths, checking connectivity. Mathematical problems, definitions like factorial, Fibonacci sequence, or generating sequences. Parsing, breaking down complex expressions or text. When your problem can be easily defined in terms of a smaller version of itself, recursion is usually the most elegant and functional solution. Conclusion: recursion is a cornerstone of functional programming, allowing us to achieve repetition and process vast amounts of data without resorting to mutable state and its associated complexities. By understanding its two core components, the base case and the recursive step, you can unlock a powerful and elegant method of problem solving. While initial concerns about stack overflow are valid, recognizing the role of tail call optimization demonstrates how functional languages mitigate these practical issues. In the next chapter, we'll delve deeper into how functional programming manages the inevitable need to interact with the outside world, dealing with state and side effects in a principled way that preserves purity. Chapter 5. Managing State and Side Effects, the FP Approach. In the last few chapters, we've celebrated the virtues of pure functions and immutability. We've seen how they lead to predictable, testable, and parallel-friendly code. But let's be honest, a perfect world of only pure functions is a programmer's utopia. In reality, programs have to do impure things to be useful. They need to read user input, write to files, send data over the internet, display things on a screen, and interact with databases. These are all examples of side effects. So, how does functional programming reconcile its core philosophy of purity with the undeniable need to perform side effects and manage state that changes over time? The answer isn't to eliminate side effects entirely, but to approach them with a strict, disciplined strategy. Isolate, represent, and manage. The problem with uncontrolled side effects, revisited. We touched on this briefly, but it's worth reiterating. Uncontrolled side effects are the bane of robust software. When any part of your program can at any time modify global variables, write to external systems, or engage in unpredictable input-output operations, you quickly lose control. Consider this scenario. You have a function that calculates a financial transaction. Ideally, this should be a pure calculation. But what if, within that same function, it also logs the transaction to a file, updates a database record, and sends a notification email? Testing becomes a nightmare. To test the calculation, you now also have to worry about the file system, the database state, and whether an email was sent. Concurrency is fraught with peril. If two transactions happen simultaneously, who writes to the file first? Who updates the database record? The order might be arbitrary, leading to corrupted data or incorrect results. Debugging is a treasure hunt. If a problem occurs, it's hard to tell if the calculation was wrong, the file write failed, the database update didn't commit, or the email just vanished. The core of functional programming's solution is to say, these messy, unpredictable operations are necessary, but we will not let them infect our beautiful, pure code. The FP solution: isolate, represent, and execute. The functional approach to state and side effects can be summarized in 3 key steps. 1. Isolate the impure parts. The first rule is to keep your core logic as pure as possible. The vast majority of your program's code, especially its fundamental business rules and transformations, should consist of pure functions that take inputs and produce outputs without any external interactions. Side effects are pushed to the edges or boundaries of your application. Think of it like a neatly organized kitchen. All the messy, unpredictable parts, like preparing raw ingredients, washing dishes, are confined to specific areas. The act of actual cooking, your pure computations, happens in a clean, controlled environment. 2 represent side effects as data recipes for action. This is a key insight. Instead of doing a side effect immediately, you describe the side effect you intend to perform. You create a recipe or a plan for action, which is itself pure data. Imagine you're the head chef and you have several line cooks. In an imperative kitchen, you might constantly yell commands. Chop the onions, sauté the chicken, plate the pasta. You're directly executing instructions and managing state, the dishes cooking on the stove. In a functional kitchen, you'd instead write down a detailed to-do list or recipe book for your cooks. This recipe book describes all the steps. Step 1, get onions. Step 2, slice onions. Step 3, put cooked onions in this bowl. The recipe itself is just information on a piece of paper, immutable data. It doesn't actually chop any onions, it merely describes the action of chopping. Similarly, in functional programming, a function that might have a side effect doesn't just perform it. Instead, it returns a data structure that represents the intended side effect. For instance, instead of save to database data, a pure function might return an object like action. Type SAVETODB payload data. This object is just data, it's a pure value. It's a declarative instruction. This recipe approach means the function that produced the recipe is pure. It just calculates a description based on its inputs. The recipe itself is immutable data. You can inspect it, pass it around, or combine it with other recipes without any actual side effects occurring. 3. Execute the side effects at the edge. Once you have your pure description of the side effect, your recipe, something eventually needs to execute it. This happens at the very boundary or edge of your system. There's usually a small, dedicated part of the application whose job it is to take these recipes for action and actually perform the dirty work. Interact with the database, send the email, print to the screen. Going back to our kitchen analogy, you, the head chef, hand your complete recipe book to the line cooks. The line cooks are the executors. They are the only ones allowed to interact with the raw food, the hot stoves, and the dirty dishes. You, the head chef, remain in your pure, planning world, composing recipes, managing state through transformation. Even with immutable data, programs evolve over time. How do you represent a user's changing profile or the progression of an order through an e-commerce system? Functional programming handles this by treating state not as a single, mutable entity, but as a sequence of transformations. Instead of current profile age equals 30, modifying the profile in place, you would think of it as new profile equals update age, current profile 30, producing a new profile based on the old one. Each change generates a new version of the state. The program's ongoing state becomes a chronological chain of immutable snapshots. State 1, state 2. This approach is particularly powerful for auditing and debugging. You have a complete history of how the state evolved. You can time travel through your application's state to see exactly what happened at any point. Undo-redo functionality. Trivial to implement because you just revert to a previous immutable state in the chain. Concurrency. Multiple operations can work with different historical versions of the state, then combine their results into a new shared state without race conditions. Some functional programming systems build on this by using event sourcing, where every change is recorded as an immutable event, like a log entry. User X updated profile. Item Y added to cart. The current state is then derived by replaying all relevant events. This allows for incredibly robust, auditable, and eventually consistent systems. The functional mindset for effects. This approach shifts your mindset from doing to describing. Instead of, go fetch data from the internet, you think, compose a description of how to fetch data from the internet. Instead of, change the user's name in the database, you think, create an immutable instruction to change the user's name. which an external system will eventually execute. This discipline of separating pure computations from impure actions is one of the most powerful and insightful contributions of functional programming. It allows you to build a reliable and testable core for your application, where logic is clear and predictable, while still providing all the necessary functionality to interact with the messy, real world. The complexity of side effects is not eliminated, but it is explicitly acknowledged, contained, and managed rather than scattered throughout your codebase. Conclusion: functional programming doesn't just ignore state and side effects, it deliberately designs around them. By isolating side effects, representing them as pure data recipes for action, and then executing them at the system's boundaries, you gain immense control, predictability, and testability. Furthermore, managing state through a series of immutable transformations, instead of in-place modifications, offers powerful benefits for debugging, auditing, and concurrency. This strategic management of the impure parts allows your functional core to remain clean, highly reliable, and easy to reason about. In the next chapter, we'll dive into specific techniques for data transformation, building on these principles to make our data manipulation both elegant and efficient. Chapter 6: Data Transformation, Mapping, Filtering, and Reducing. In the previous chapters, we've laid the groundwork for functional thinking. The purity of functions, the immutability of data, the power of functions as first-class citizens, and the discipline of managing side effects. Now, it's time to put these ideas into practice, focusing on one of the most common and crucial tasks in programming: transforming data. At the heart of many programs is the need to take some input data, change it in various ways, and produce some output data. Functional programming provides an exceptionally elegant and powerful toolkit for these transformations, primarily through the use of higher-order functions that operate on collections. We briefly introduced map, filter, and reduce in Chapter 3. But now we'll delve deeper into their practical application and understand why they are so fundamental to the functional approach to data manipulation. The functional way: declarative data pipelines. Instead of thinking about data transformation as a series of steps that modify data in place, an imperative approach, functional programming encourages a declarative mindset. You describe what you want the final data to look like, or what criteria it should meet, rather than specifying the exact, step-by-step instructions for getting there. This leads to data pipelines, where data flows through a series of pure transformations, much like a factory assembly line. Each stage takes an input, applies a pure function, and produces an output for the next stage. The key benefits of this approach are immutability. Each transformation generates new data, leaving the original data untouched. This provides predictability and safety, especially in concurrent environments. Readability. The declarative nature often makes the code clearer, focusing on the purpose of the transformation rather than its mechanics. Composability. Transformations can be chained together easily, building complex operations from simple, reusable functions. Let's revisit our core trio: map, filter, and reduce. Map, transforming each element individually. As we discussed, map applies a transformation function to every element in a collection and returns a new collection containing the transformed elements. Why is map so useful? Standardizing data. Suppose you receive data where prices are strings, but you need them as numbers. A map function with a string-to-number conversion function can clean up the entire list in one go. Preparing for display, you have a list of user objects, but for display, you only need their full names formatted. Map can transform a list of first name, John, last name, Doe, objects into John Doe, Jane Smith. Scaling values. Adjusting all scores in a game, converting temperatures, scaling images for display, map is perfect for any scenario where each item needs the same type of individual adjustment. Analogy. The photocopy machine. Think of map as a specialized photocopy machine. You feed in the original documents, your list of data, and it makes a perfect copy of each one, but it also applies a consistent transformation as it copies. For example, if your machine is set to enlarge by 20%, every copied document will be 20% larger. The original documents remain untouched. Filter. Selecting elements based on a condition. filter creates a new collection containing only the elements from the original collection that satisfy a given condition. Why is filter incredibly powerful? Subsetting data. From a list of employees, you might only want managers or employees who have been with the company for more than 5 years. Data validation. You have a list of user inputs and need to remove all invalid entries. Filter can keep only the inputs that pass your validation logic. Security and permissions, displaying only the content a user is authorized to see from a larger dataset. Analogy. The quality control inspector. Imagine an inspector on an assembly line. Items pass by, and the inspector has a checklist of criteria. If an item meets the criteria, it's allowed to proceed to the next stage. Otherwise, it's discarded. Filter acts as this inspector, creating a new collection of only the approved items. Reduce or fold, aggregating and combining elements. Reduce is arguably the most versatile of the three. It takes a collection of data and boils it down to a single value by repeatedly applying a combining function. How is reduce so versatile? While map and filter always return a collection of the same size, for map, or smaller, for filter, reduce can return any type of single value. A sum, an average, a count, a single formatted string, or even a completely new data structure like an object or a dictionary. Calculating aggregates, summing numbers, finding the maximum-minimum value, calculating an average. Building complex data structures, grouping items by a certain key into a dictionary, creating a hierarchical structure from a flat list, or parsing a complex log file into a summary object. Composing operations. Interestingly, both map and filter can actually be implemented using reduce, demonstrating its fundamental nature. Analogy. The master chef's stock pot. Think of reduce as a large stock pot in a kitchen. You throw in various ingredients, your data elements, and you know your intention is to end up with a single, flavorful stock. Each time you add an ingredient, you stir and combine your reducer function, blending that new ingredient with everything already in the pot, until ultimately, all ingredients have contributed to the final, single product, your rich stock. Chaining transformations, building data pipelines. One of the most powerful aspects of these functions in functional programming is how easily they can be chained together to form clear, readable data processing pipelines. Since each function returns a new collection, the output of one can seamlessly become the input of the next. Consider a scenario. You have a list of sales transactions. You want to find the total revenue from all transactions that occurred in January and were over $100. In an imperative style, you might use several nested loops or a series of temporary variables. Initialize total revenue equals 0. Loop through all transactions. Inside the loop, check if the transaction date is in January. If it is, check if the amount is over $100. If both conditions are true, add the amount to total revenue. In a functional, chained approach, it would look more like this. Transactions. Filter by January date. Filter by amount over $100. Map to just the amount if transaction object is complex. Reduce by summing amounts. Each step is a pure transformation, making the process clear and preventing inadvertent modifications to the original sales data. The readability of this pipeline style, moving from left to right or top to bottom, often mirrors how we think about data transformations. The power of abstraction. What map, filter, and reduce truly offer is a powerful level of abstraction. Instead of focusing on the mechanics of how to iterate over a collection, which indices, which loop variables, when to break, you focus on what you want to achieve. This frees you from boilerplate code and allows you to concentrate on the business logic unique to your problem. This declarative, pipeline-oriented approach to data transformation is not just aesthetically pleasing, it's robust. Because each step is pure and produces new, immutable data, you gain all the benefits we've discussed. Easier testing, safer concurrency, and clearer code that is less prone to bugs. Conclusion: data transformation is central to almost all software, and functional programming provides an elegant, powerful, and safe way to handle it. By mastering higher-order functions like map, filter, and reduce, you can create clear, composable, and immutable data pipelines. These tools allow you to describe complex transformations declaratively, making your code more readable, testable, and robust. In the next chapter, we'll expand on this idea, exploring how functions can be composed and executed in sequences, building even more sophisticated operations. Chapter 7, Function Composition and Pipelining, Building Blocks of FP. We've explored how functional programming emphasizes pure functions, immutable data, and powerful higher-order functions for data transformations. Now, let's look at how these pieces fit together to build sophisticated, maintainable programs. The secret lies in function composition and pipelining techniques that allow you to combine small, focused functions into larger, more complex ones, much like snapping Lego bricks together to create an elaborate structure. The idea of composition, building from simple parts. At its core, composition is about combining simpler functions to form a more complicated function. In mathematics, if you have functions f, x, and g, x, their composition fg, x means applying g to x first, and then applying f to the result of g, x. So fg, x equals f, g, x. Functional programming brings this mathematical concept directly into code. Instead of writing one giant function that does everything, you break down a complex task into a series of smaller, single-purpose functions. Each of these smaller functions does one thing well, takes a specific input, and produces a specific output. Then you combine them. Why compose functions? Readability. Composed functions often read like a description of the problem. First do this, then do that, then do the other. Reusability. Small, single-purpose functions are highly reusable. You can mix and match them to solve different problems without rewriting code. Testability. Since each component function is pure and does just one thing, testing them individually is straightforward. If a composed function isn't working, you can quickly find the faulty component. Maintainability. Changes to one part of the logic are isolated to a single, small function, reducing the risk of unintended consequences in other parts of the system. Pipelining. The flow of data. Pipelining is a common pattern for function composition, especially when dealing with sequences of data transformations. It emphasizes the flow of data through a series of functions, where the output of one function becomes the input for the next. This creates a clear left-to-right, or top-to-bottom, chain of operations that mirrors how you might describe a process. Let's revisit our example from the previous chapter, finding the total revenue from January transactions over $100. Instead of an imperative approach, we imagined a functional pipeline. Start with transactions. Filter for January dates. Filter for amounts over $100. Map to extract just the amount. Reduce to sum the amounts. This sequence is a perfect example of a data pipeline. Each step is a function that takes the output of the previous step as its input. Imagine data moving through a series of specialized machines on an assembly line. The output from machine A goes directly into machine B, then machine B's output goes to machine C, and so on. Each machine performs a specific, isolated task, and together, they produce the final product. Tools for composition, pipe and compose. While you can manually chain functions by nesting calls, e.g., reduce, map, filter data, this quickly becomes hard to read, especially when many functions are involved, as it forces you to read from the inside out. Functional programming languages and libraries often provide special utilities for composition, commonly named pipe or flow and compose. Pipe or flow reads left to right. Pipe FGH means H, G, F, X. It's like our assembly line. X goes to F, F's result goes to G, G's result goes to H. This maps directly to the human thought process of first do this, then that. Compose reads right to left the mathematical way. Compose, FGH means F, G, H, X. The input X first goes to H, then H's result goes to G, then G's result goes to F. Some find this more intuitive when thinking about building up operations from the base. While they achieve the same end, pipe is generally preferred for its improved readability, making the flow of data more intuitive for most programmers. Let's illustrate the difference conceptually for a simple operation. Double then add 1. Without composition nested calls, add 1 double x. Using pipe, pipe double add 1 x. Using compose, compose add 1 double x. In the pipe example, the order of functions double. Add 1 directly reflects the order of operations. This readability greatly enhances understanding, especially for complex data pipelines. Currying and partial application, making functions more composable. To further facilitate composition, functional programming often leverages techniques like currying and partial application. These concepts help transform functions to make them more amenable to being chained and reused. Currying. Currying is the process of transforming a function that takes multiple arguments into a sequence of functions, each taking a single argument. For instance, a function add x, y that takes x and y and returns their sum could be curried into add x, y. When you call add 3, it doesn't return a number. It returns a new function that is waiting for its second argument. When you then call the new function, 5, it returns 8. Analogy: imagine a multi-stage vending machine. Instead of pressing buttons for large coffee all at once, you first press large, and the machine waits for you to pick coffee. Each selection gives you a new, more specialized machine until you have the final product. Partial application. Partial application is closely related to currying. It's the process of applying a function to some, but not all, of its arguments, resulting in a new function that expects the remaining arguments. For example, if you have a general greeter, greeting phrase, name, function, you could partially apply it to create a say hello equals greeter, hello, function. Say hello is now a new function that only takes a name as an argument. How do they help composition? Creating specialized functions. Currying and partial application allow you to create new, more specialized functions on the fly. For instance, if you have a filter function and want a common is-even filter, you can partially apply a modulo function to 2, enabling point-free style. Functions that are partially applied or curried become easier to pipe or compose because they often result in functions that take a single argument and return a single result. This allows for a point-free style, where you don't explicitly mention the data being transformed, letting the pipeline elegantly describe the transformation itself. For example, instead of numbers, map n equals double n, you might simply write numbers map double. Real-world application, HTTP request handling. Consider an example of processing an HTTP request in a web server or client. You might have a series of small, composable functions. Parse request takes a raw request string, returns a structured data object. Authenticate user takes the parsed request, adds user authentication details if valid, returns updated request or error. Validate data validates inputs within the request object, returns updated request or error. Process payment. If data is valid, processes payment and returns a payment result. Send response takes the final result, formats it, and sends it back to the client. A functional approach would pipe these functions together. If any function in the pipeline encounters an issue, e.g., authentication fails, data is invalid, it can stop the pipeline or return a specific error value that subsequent functions can handle gracefully. This leads to a very clear flow of control and error handling. Conclusion: function composition and pipelining are at the heart of building robust and expressive functional programs. By breaking down complex problems into small, pure, and reusable functions, and then combining them using techniques like pipe and compose, you create code that is incredibly clear, testable, and maintainable. Currying and partial application further enhance this composability, allowing for elegant, point-free style programming. This ability to assemble powerful solutions from simple, predictable components is a hallmark of functional thinking, and it leads to software that is not only correct, but also a pleasure to build and understand. Next, we will explore patterns for handling complex data structures within this functional paradigm. Chapter 8, Pattern Matching and Algebraic Data Types, Elegant Data Handling. So far, we've focused heavily on functions and how they transform data. But what about the data itself? Functional programming often employs powerful concepts for defining and working with data structures that go beyond simple numbers and strings. Two key ideas in this realm are algebraic data types, ADTS, and pattern matching, which together provide an elegant, safe, and expressive way to handle various forms of data. The problem with null or undefined. In many traditional programming languages, a common source of bugs is the concept of a null or undefined value. If a function expects a string but receives null or an object but receives undefined, it can lead to runtime errors, the dreaded null pointer exception that has plagued programmers for decades. These kinds of errors often occur because the type system of the language doesn't explicitly guarantee that a value will always be present. And it's up to the programmer to remember to check for null or undefined everywhere. Functional programming, particularly in languages designed with strong type systems like Haskell or Scala, offers a more robust solution by explicitly modeling the presence or absence of data within the type system itself, using algebraic data types and handling them with pattern matching. Algebraic data types, ADTs, explicitly modeling data shapes. Algebraic data types allow you to define data structures very precisely, stating not just what values they hold, but also what their possible forms or variations are. They are called algebraic because their structure often mirrors algebraic expressions. There are two main kinds of ADTs. One sum types, also called tagged unions or disjoint unions. A sum type allows a value to be one of several possibilities. The name sum comes from the idea that the total number of possible values for a sum type is the sum of the possible values of its constituent types. Analogy, a status field. Imagine you're building a system to track the status of an operation. It could be success, failure, or pending. In traditional programming, you might use strings, success, failure, pending, or integer codes 1, 0, -1. But what if you misspell a string or use the wrong integer? The compiler won't catch it. A sum type for status would make this explicit. Status can be either success or failure or pending. Handling optional values safely. This is where sum types really shine. Instead of null, many functional languages have an option or maybe type. Option can be either some value or none. If you have an option string, it means you either have a string wrapped in some, or you explicitly have none, meaning no value is present. A function declared to return option string clearly communicates that a string might not always be there, forcing the calling code to handle both possibilities. This eliminates null pointer errors, representing errors. Similarly, an either or result type can represent an operation that might either succeed, producing a right value, often the expected result, or fail, producing a left value, often an error message. Either error, value can be either left, error, or right value. Again, this explicitly pushes error handling into your type system, ensuring you can't forget to handle the failure case. 2. Product types, also called records or structs. A product type allows a value to be composed of multiple specific values simultaneously. The name product comes from the idea that the total number of possible values for a product type is the product of the possible values of its constituent types. Analogy, a person record. A person type might be composed of a name and an age and a gender. All three fields must be present and valid for it to be a complete person record. Example, user has a username and an email and a creation date. In essence, ADTs give you a powerful and type-safe way to model your domain, express clearly what your data is and what forms it can take. Pattern matching, deconstructing data elegantly. Once you've defined your data using ADTs, pattern matching is the mechanism used to elegantly and safely inspect these data structures and extract their contents. It's like a highly intelligent switch statement, but for data shapes instead of just simple values. With pattern matching, you define different patterns that your data might conform to. When a value is provided, the system checks which pattern it matches. Once a match is found, specific code associated with that pattern is executed, and you can conveniently extract the values directly from within that pattern. How pattern matching works: consider our option type, some value or none. If you have an option string, you can use pattern matching to handle both cases. If it matches the sum's pattern, you know a value is present, and you can directly access that string as S within the sum branch of your code. If it matches the none pattern, you know no value is present, and you can handle that specific case, e.g., provide a default, log an error. This forces you to explicitly consider all possible forms of an ADT, making your code safer. If you forget to handle one of the cases in a sum type, the compiler will often warn you. This eliminates an entire class of runtime errors that are common in less expressive languages. Example, processing different event types. Imagine your system processes various event types: user logged in, order placed, payment failed. Using ADTS, you might define event as a sum type. Event can be either user logged in username, timestamp, or order placed, order ID, customer ID, amount, or payment failed, order ID, reason. With pattern matching, a function that processes an event could look like this. When processing an event, if the event is user logged in, user time, log that user logged in at time. If the event is order placed, D, customer price. Update the database with ID and customer process price. If the event is payment failed, ID, cause, send alert for ID payment failure due to cause, notify customer. Each if clause, which is how pattern matches are often conceptually represented, clearly defines what to do based on the shape and contents of the event. Benefits of ADTS and pattern matching. Type safety and robustness. Explicitly modeling possibilities. Option. Either, enforcing exhaustive pattern matching effectively eliminates null pointer exceptions and ensures all cases are handled. The compiler becomes your diligent assistant, catching potential errors at compile time instead of letting them surface at runtime. Clarity and expressiveness. ADTS let you model your domain incredibly precisely. Pattern matching then provides a very readable and structured way to deconstruct and react to different data shapes. The code often reads like a direct translation of your business rules. Easier refactoring. If you add a new case to a sum type, e.g., a new payment refunded event, the compiler will immediately tell you every place in your code where you are pattern matching on events that now needs to handle the new payment refunded case. This makes refactoring and extending your codebase much safer and more efficient. Immutability support. ADTS are inherently immutable. When you match on a pattern, you are inspecting the data, not changing it. Any transformation would produce a new ADT instance. Conclusion. Algebraic data types and pattern matching are powerful allies in functional programming, offering a principled and elegant approach to data modeling and manipulation. By declaring data types that precisely represent all possible variations, and then using pattern matching to safely and exhaustively handle each of these variations, you build applications that are more robust, easier to reason about, and significantly less prone to common runtime errors. This focus on clear data definitions complements the emphasis on pure functions, allowing you to compose not just behaviors, but also highly reliable data flows. Chapter 9. The Illusion of Order. Dealing with concurrency and FP. The world we live in is inherently parallel. Many things happen at the same time. Cars drive, clocks tick, conversations flow, and countless systems compute independently. Yet for decades, most programming was designed around a sequential execution model. First line A, then line B, then line C. This worked well as long as processors kept getting faster, allowing sequential programs to run quicker. However, as we discussed in Chapter 1, that changed. Processors stopped getting dramatically faster and started getting more numerous multi-core systems became the norm. To harness this power, programs need to perform tasks concurrently, running multiple operations seemingly, or actually, at the same time. This is where traditional imperative and object-oriented programming often run into their biggest headaches, and where functional programming really shines. The concurrency problem, shared mutable state. The primary source of pain in concurrent programming in traditional paradigms is shared mutable state. Imagine a single whiteboard. If multiple people are trying to read from it and write to it simultaneously, without coordination, you quickly end up with garbled information. Writes can overwrite each other, reads can happen while data is half updated, and the whole system becomes unpredictable. This leads to insidious bugs like race conditions, deadlocks, and live locks, which are notoriously difficult to reproduce, diagnose, and fix. To cope with this, imperative programmers typically resort to locks, like mutexes or semaphores. These are mechanisms that ensure only one thread, a sequence of instructions running concurrently, can access a particular piece of shared data at a time. While locks prevent data corruption, they introduce their own set of problems. Performance bottlenecks. Locks inherently serialize access, meaning only one thread can proceed, defeating the purpose of concurrency for that section of code. Complexity. Deciding what to lock, when to lock it, and for how long is a subtle art. Misuse can lead to deadlocks, where threads endlessly wait for each other, or live locks, where threads constantly yield to each other without making progress. Debugging nightmare. Concurrency bugs are non-deterministic, meaning they might only appear under specific, hard-to-reproduce timing conditions. Functional programming solution. Embrace immutability. Functional programming doesn't try to solve the problem of shared mutable state by adding more rules or tools, like locks, to manage it. Instead, it largely eliminates the problem itself through its core principles. Immutability. If data, once created, can never be changed, then there's no shared mutable state to worry about. Multiple concurrent operations can safely read the same immutable data without any risk of one operation unexpectedly changing the data that another operation is currently using. It's like everyone having their own copy of the blueprint. They can read it as much as they want, and if they need to update it, they produce a new version of the blueprint, leaving the original intact. Pure functions. Since pure functions only depend on their inputs and produce no side effects, their execution order doesn't matter from a correctness standpoint. Two pure functions can run completely in parallel, and their results will be consistent regardless of which one finishes first. There's no hidden interaction to cause problems. This fundamental shift makes concurrent programming vastly simpler and safer. The functional programmer no longer spends their time managing locks or grappling with race conditions. Instead, they focus on defining clear transformations between immutable data. Concurrency patterns in FP. While immutability and purity simplify concurrency, functional programming also offers powerful patterns and abstractions for orchestrating concurrent tasks when interaction with the outside. Impure, world is necessary. 1. Parallel map filter reduce. Because pure functions that operate on collections, map, filter, reduce, don't have side effects and don't mutate the collection itself, they are inherently easy to parallelize. For example, parallel map. If you need to double every number in a very large list, you can split the list into smaller chunks, apply the doubling function to each chunk concurrently on different processors, and then combine the results. No locking is required because each processor is working on its own separate piece of data and producing a new, distinct result. Parallel filter reduce. Similar principles apply. These operations are often referred to as embarrassingly parallel because of how easily they can be distributed across multiple cores or even multiple machines. 2. Actor model. While not exclusively functional, the actor model aligns very well with functional principles and is a popular choice for concurrent, distributed systems. In the actor model, actors are independent, isolated entities that encapsulate their own state. They communicate with each other only by sending and receiving immutable messages. An actor processes one message at a time, preventing internal race conditions. When an actor receives a message, it can update its own internal state, send messages to other actors, or create new actors. The key is that an actor's internal state is effectively not shared mutably with the outside world. It's carefully managed internally, and external interaction happens via immutable messages. This provides a formal, structured way to handle mutable state within an otherwise immutable and pure paradigm, making it much easier to build robust and scalable concurrent systems. Languages like Erlang, a purely functional language, and frameworks like Akka, for Scala and Java, are famous for their robust implementations of the actor model 3. Software transactional memory, SDM, for situations where you must have shared mutable state, e.g., a shared counter or a global configuration. Some functional languages offer software transactional memory, SDM. SDM is a concurrency control mechanism inspired by database transactions. How SDM works conceptually, you declare certain pieces of state as transactional. Any operation that modifies this transactional state runs inside a transaction. The system guarantees that either the entire transaction completes successfully, commits, or it fails entirely, aborts, ensuring atomicity. If two transactions try to modify the same transactional state concurrently, the system will detect this conflict and automatically retry one of the transactions until it succeeds without conflict. Programmers don't need to manually acquire or release locks. The SDM system handles this automatically and transparently. This significantly reduces the complexity associated with managing shared mutable state in a concurrent environment, pushing the burden from the programmer to the runtime system. Clojure, a modern Lisp dialect, is a prominent example of a language that heavily utilizes SDM for managing concurrent shared state. The illusion of order. The title of this chapter, The Illusion of Order, refers to the fact that while our minds often think sequentially, the physical world and multi-core processors operates in parallel. Functional programming embraces this inherent parallelism by removing the very thing that makes concurrent programming hard: mutable shared state. It shifts the paradigm from, how do I correctly orchestrate multiple threads, all trying to change the same thing, to, how do I define a series of immutable transformations that can be performed independently on different data segments, and then combine their results? This approach isn't just about avoiding bugs. It's about making concurrent thinking a natural extension of functional thinking. When your building blocks are independent, testable, and free of side effects, combining them to work simultaneously becomes far simpler and less error-prone. Conclusion: the rise of multi-core processors and distributed systems has made concurrent programming an essential skill. But its complexities are a major source of bugs and development friction in traditional paradigms. Functional programming offers a powerful solution by fundamentally redesigning how we approach state and side effects. By prioritizing immutability and pure functions, it sidesteps many of the common pitfalls of concurrency. Furthermore, patterns like the actor model and software transactional memory provide robust, high-level abstractions for managing interactions with the unavoidable mutable aspects of the real world. This makes functional programming an incredibly appealing paradigm for building scalable, reliable applications in today's increasingly concurrent computing landscape. Chapter 10. Functional Languages in Practice. A glimpse into the ecosystem. We've delved into the core concepts of functional programming, understanding what it is and why it's beneficial. Now, let's explore where these ideas are put into practice. While functional programming principles can be applied to some extent in almost any language, certain programming languages are designed from the ground up to embody and prioritize the functional paradigm. These are often categorized as purely functional or multi-paradigm with strong FP support. This chapter will introduce you to a few prominent functional languages, highlighting their design philosophies and where they excel. This isn't an exhaustive list or a tutorial, but rather a tour of the functional ecosystem to illustrate the diversity and applicability of FP concepts. Purely functional languages. The uncompromising path. These languages enforce functional principles very strictly, often making it difficult or impossible to write code that violates immutability or introduces uncontrolled side effects. This strictness provides powerful guarantees about predictability and correctness. Haskell, the academic and theoretical powerhouse. Design philosophy. Haskell is a purely functional, statically typed language known for its strong mathematical foundations. It enforces purity rigorously, using advanced type system features, like monads, which we won't deep dive into, but are a way to manage side effects in a pure context to handle interactions with the outside world. It also features lazy evaluation, meaning expressions are only computed when their results are actually needed. Where it excels: correctness and reliability. Its strong type system catches a vast array of errors at compile time, leading to highly reliable software. Prototyping and research. Its expressiveness and power make it a favorite in academic research, particularly in areas like language design, formal verification, and advanced type theory. Concurrency. Its inherent purity and immutability make concurrent programming simpler and safer. Domain-specific languages, DSLs. Its flexibility in defining new syntax makes it excellent for creating highly specialized languages. Known for challenging learning curve due to advanced abstract concepts, but incredibly rewarding for those who persevere. Its type system is often seen as both its most intimidating and most powerful feature. Erlang, concurrency and fault tolerance champion. Design philosophy. Developed by Ericsson for building highly reliable, fault-tolerant, distributed systems capable of handling massive concurrency, like telecommunication switches. Erlang's core philosophy is let it crash. Rather than preventing errors, it provides mechanisms for systems to automatically recover from failures. It achieves concurrency through its actor model, as discussed in Chapter 9, where lightweight processes communicate via asynchronous message passing. Where it excels, massive concurrency, handles hundreds of thousands or even millions of concurrent connections effortlessly. Fault tolerance. Systems can be built to continue operating even if individual components fail. Distributed systems, designed from the ground up for networked distributed applications. Hot code swapping, ability to update running code without downtime. Known for its unique syntax and runtime characteristics, built for industrial-grade reliability. WhatsApp famously used Erlang to handle its immense user base. Multi-paradigm languages with strong FP support. Pragmatic adoption. These languages aren't strictly functional, but they deeply integrate functional programming concepts alongside object-oriented or imperative features. This allows developers to gradually adopt FP patterns and build hybrid solutions, often making them more accessible to those coming from traditional backgrounds. Scala, bridging OOP and FP. Design philosophy. Scala, scalable language, aims to combine the best features of object-oriented and functional programming. It runs on the Java Virtual Machine, JVM, allowing seamless interoperability with the vast Java ecosystem and libraries. It encourages immutable data structures and highly favors pure functions. Where it excels, big data processing, widely used in big data ecosystems, especially with frameworks like Apache Spark, due to its ability to handle large-scale concurrent data transformations elegantly. Hybrid applications allows developers to choose the best paradigm for each part of their application or seamlessly blend them. High performance, leveraging the JVM provides strong performance characteristics. Known for its powerful type inference, expressive syntax, and the ability to write very concise yet robust code. Some find its flexibility also makes it more complex to master. Clojure, Lisp reimagined for the JVM. Design philosophy. Clojure is a modern dialect of Lisp, a language with deep functional roots, running on the JVM. It strongly emphasizes immutability, pure functions, and concurrency through its software transactional memory, SDM, system and persistent data structures. Its syntax is very minimalistic, based on parentheses and highly expressive. Where it excels, concurrency, designed for concurrency from the ground up, providing robust primitives. Interactive development. Its REPL-driven development style, read-eval print loop, makes for extremely fast feedback and exploration. Data transformation. Highly effective for complex data manipulation due to its powerful collection libraries and emphasis on immutable data. Interoperability seamlessly integrates with Java libraries. Known for its elegant simplicity, powerful macro system, allowing for language extension, and strong community around functional programming principles. #f#, functional programming on net. Design philosophy. F# is Microsoft's functional first language for the .NET platform. It blends functional, object-oriented, and imperative programming, but strongly champions functional paradigms. It boasts a powerful type inference system, making code often look more concise than C. Where it excels, data science and analytics, strong support for data manipulation, numerical computing, and machine learning. Web development with Safe Stack, building full-stack web applications with functional principles. General-purpose programming can be used for a wide range of applications from scripting to enterprise solutions within the .NET ecosystem. Known for its succinct syntax, strong typing, and excellent tooling support from Microsoft Visual Studio. The functional influence on mainstream languages. Beyond dedicated functional languages, the influence of functional programming can be seen pervading historically imperative or object-oriented languages. This isn't a coincidence. It's a testament to the power and utility of functional constructs. JavaScript. With the introduction of arrow functions, map, filter, reduce, and the widespread adoption of patterns like React and Redux, which are heavily inspired by functional ideas, JavaScript developers are increasingly using functional styles. Python, features like map, filter, functools, and list comprehensions enable expressive functional patterns. Immutability is also encouraged through tuples and frozen sets. Java. Recent versions have introduced Streams API, Lambda expressions, and method references, making functional programming patterns much more accessible and idiomatic. C#. Similar to Java, C# has incorporated Lambda expressions, LINQ language integrated query, a powerful declarative query abstraction, and expression trees, allowing for functional styles. C++. C++ has long had support for functional features through the standard library, e.g., algorithms like std, transform std, accumulate, and modern C++ has enhanced this with lambdas. This cross-pollination of ideas means that even if you don't write exclusively in a functional language, understanding functional programming empowers you to write better, cleaner, and more robust code in almost any modern programming environment. Conclusion: the landscape of functional programming languages is rich and diverse, spanning from the rigorously pure to the pragmatically multi-paradigm. Each serves different niches and offers unique strengths, whether it's unyielding correctness, unparalleled concurrency, or seamless integration with established ecosystems. But more importantly, the core principles of functional programming have proven so valuable that they are now influencing the design and usage of nearly every mainstream language. This suggests that functional thinking is not just a niche skill, but a powerful and increasingly essential mindset for any modern programmer, regardless of their chosen tool. In the next chapter, we'll look at specific examples of how these principles are applied in real-world scenarios. Chapter 11: Functional Programming in the Real World. Case Studies and Applications. By now, you understand the core tenets of functional programming and why they matter conceptually. But is it just a theoretical exercise, or is functional programming truly making a difference in the trenches of real-world software development? The answer is a resounding yes. From financial trading platforms to massive online messaging systems and cutting-edge data analysis tools, functional programming has proven its value in diverse and demanding applications. This chapter will explore several real-world case studies and application areas where functional programming principles have been successfully applied, often leading to more robust, scalable, and maintainable systems. Case Study 1: Financial Systems, Reliability and Precision. The finance industry is perhaps one of the most demanding environments for software. Billions of dollars can hinge on the correctness and reliability of a system. Bugs are not just inconvenient, they can be catastrophic. Accuracy, predictability, and the ability to audit every change are paramount. This is an environment where functional programming thrives. Why FP fits immutability. Financial transactions, ledgers, and market data are inherently immutable. Once a trade is executed or a price is recorded, it should not change. FP's emphasis on immutable data structures naturally aligns with this requirement, making it easier to track and audit every state change as a new, distinct record. Purity, core financial calculations, e.g., option pricing, risk assessment, should ideally be pure functions. Given the same inputs, they must always produce the same, precise output. This makes them highly testable and verifiable. Concurrency. High-frequency trading and real-time market data processing involve massive amounts of concurrent operations. FP solutions to concurrency, like Actors or SDM, help manage this complexity without the pitfalls of shared mutable state. Real-world examples. Many quantitative finance platforms and trading systems, particularly those dealing with complex derivatives or requiring high levels of precision and auditability, leverage functional languages like Haskell or F. The guarantees of correctness and the composability of pure functions significantly reduce the risk of costly errors. Investment banks and hedge funds often employ functional languages for their analytical backends. Case Study 2: Distributed Systems and Concurrency, Scaling for the Masses. As we discussed, the shift to multi-core processors and the need for scalable web services have made concurrent, and distributed programming a critical skill. This is where functional programming, especially languages designed with concurrency in mind, excels. Why FP fits immutable data, the primary reason. When data is immutable, you don't need locks or complex synchronization primitives to safely share it across different threads or even different machines. Actor Model SDM. Languages like Erlang and Clojure provide built-in, first-class support for managing concurrent processes and shared state in a safe and structured manner, making it easier to build systems that can scale horizontally and recover gracefully from failures. Real-world examples. WhatsApp famously relied on Erlang for its backend infrastructure to handle its massive number of concurrent users and messages. Erlang's fault tolerance and concurrency features were key to WhatsApp's ability to scale quickly and reliably with a relatively small team. Web services. Many modern backend services and APIs, especially those built using frameworks that support functional paradigms, like Scala plus Akka, or various functional Python/Node.js frameworks, benefit from the clarity and safety of functional concurrency patterns. Case Study 3. Big Data Processing and Analytics, Taming the Data Deluge. The sheer volume and velocity of data in today's world demand robust and efficient processing solutions. Functional programming patterns are a natural fit for distributed data processing. Why FP fits? Map, filter, reduce. The core operations of distributed data processing frameworks like Hadoop and Apache Spark are directly inspired by the functional map, filter, and reduce concepts. These pipelines inherently lend themselves to parallel execution across clusters of machines. Immutability. In a distributed setting, ensuring data consistency is crucial. Immutable data structures simplify this by eliminating the need for complex distributed locking mechanisms. Each transformation simply produces a new, updated version of the dataset. Declarative style. Describing what data transformations should occur, e.g., group by customer ID, then sum total purchases. Rather than how to iterate over massive datasets, allows these frameworks to optimize execution across distributed nodes. Real-world examples. Apache Spark, a leading big data processing engine, widely adopted across industries, is written primarily in Scala, a hybrid functional OO language. Its core programming model for data transformations directly reflects functional patterns like map, filter, and reduce. Companies like Netflix, Uber, and Airbnb heavily use Spark for analytics, machine learning, and data pipelines. Data workflows. Many companies build internal data processing pipelines and ETL, extract, transform, load tools using functional languages or frameworks that embrace FP for managing complex data transformations. Case Study 4. Web Frontend Development, Predictable User Interfaces. Even in the traditionally imperative world of web frontends, functional programming ideas have gained significant traction, especially in how state is managed and components are rendered. Why FP fits? Predictable state management. User interfaces often involve complex, mutable state that needs to be synchronized and updated frequently. Functional patterns help make this process predictable. Pure view functions. The idea of a view being a pure function of state, given certain data, render this UI makes UIs easier to reason about and debug. Real-world examples, React and Redux. While React, a JavaScript library for building user interfaces, is not strictly functional, its core philosophy embraces functional concepts. Components are often treated as pure functions of props and state. The popular state management library Redux is heavily inspired by functional programming and immutable data. Its core principles, single source of truth, state changes via pure reducers, directly reflect FP ideas. Many major websites and applications, from Facebook to Airbnb, use React and Redux. Elm, a purely functional language specifically designed for building web user interfaces. It guarantees no runtime exceptions, making it exceptionally reliable for web applications. Functional programming in other domains. Compilers and interpreters. The transformation of source code into executable code or interpreted actions is inherently a functional problem, involving parsing, analysis, and generation, all tasks well suited to pure functions and immutable data structures. Scientific computing. The precision, testability, and composability of functional code make it attractive for numerical simulations and data modeling where correctness is paramount. DevOps and infrastructure as code. The idea of declaring infrastructure configurations, what you want the infrastructure to look like, rather than giving imperative commands, how to build it step by step, aligns well with functional principles and promotes immutability. Conclusion. The journey through these real-world applications demonstrates that functional programming is far from a niche academic pursuit. It is a powerful and increasingly vital paradigm for building modern software. Whether it's ensuring financial precision, scaling massive distributed systems, taming big data, or creating predictable user interfaces, the core principles of immutability, purity, and composability offer robust solutions to some of the most challenging problems in computing. The next time you interact with a reliable online service or a complex data-driven application, there's a good chance that functional thinking played a crucial role in its design and implementation. In our final chapter, we'll reflect on the broader implications of functional thinking beyond just writing code. Chapter 12. The Future of Functional Thinking, Beyond the Code. We've journeyed through the landscape of functional programming paradigms, from the core principles of pure functions and immutability to the elegance of composition, the safety of ADTS and pattern matching, and the power of its concurrency models. We've seen how these ideas are embodied in specialized languages and how they influence even mainstream ones, solving tangible problems in the real world. But functional thinking extends beyond just writing code. It's a mindset, a way of approaching problems that emphasizes clarity, predictability, and composability. As we look to the future, these principles, whether explicitly labeled functional or not, will become increasingly vital not just for programmers, but for anyone navigating complex systems in an interconnected world. The continued rise of functional influence. The trajectory is clear. Functional programming is not a fad. It's a fundamental evolution in how we build software. Its influence will only continue to grow for several key reasons. Processor architecture. The move towards multi-core, distributed, and eventually very high parallelism architectures, like neuromorphic computing, quantum computing, makes functional programming's models of computation, immutable data, no side effects, a natural fit. As hardware becomes more concurrent, software must follow suit, and FP provides a well-trodden path. Data explosion. The sheer volume and velocity of data in the modern world necessitate robust, scalable, and auditable data processing. Functional transformations, with their emphasis on immutable data pipelines and declarative definitions, like MapReduce, are perfectly suited for this challenge. Complexity management. Software systems are growing exponentially more complex. Functional programming offers a powerful antidote to this complexity by promoting modularity, reusability, and a high degree of testability. Pure functions act as predictable units, making large systems easier to reason about and debug. Beyond code. The functional philosophy. The underlying philosophy of FP, defining clear inputs and outputs, avoiding hidden dependencies, and focusing on predictable transformations, is applicable to many fields. Functional thinking and system design. The principles of functional programming deeply influence modern system design, even outside the direct implementation language. Microservices architectures. Microservices are often encouraged to be largely independent and stateless, communicating via well-defined APIs. This mirrors the idea of pure functions. Services take an input, process it, and return an output, minimizing shared mutable state across services. Event-driven architectures. These systems often rely on streams of immutable events, where state is derived by folding or reducing these events over time. This directly leverages the FP concept of state management through transformations on immutable logs. Version control systems, like Git. Git's core model of commits, branches, and merges inherently relies on immutable snapshots of a repository. Each commit is a new, immutable state, and changes are represented as transformations from one state to another. This is immutability in action on a grand scale. Infrastructure as code and declarative configuration. Tools like Terraform, Ansible, and Kubernetes operate on a declarative principle. You describe the desired state of your infrastructure, what you want, and the system figure out the how. This is a direct echo of declarative programming, where the focus is on results rather than step-by-step instructions. Functional thinking in everyday problem solving. The functional mindset can extend to how you approach problems in your daily life and in various non-programming domains. Clear goals and inputs. Before starting a task, clearly define what the desired outcome is, the output, and what resources or information you'll be using, the inputs. This prevents scope creep and ensures focus. Minimizing side effects in processes. In any process, whether it's organizing your home or running a team meeting, identify side effects. Things that unexpectedly modify the environment or other people's work. Try to isolate these or transform them into explicit, predictable actions. Composability in tasks. Break down large tasks into smaller, manageable subtasks. If each subtask has a clear input and output, you can combine them sequentially to achieve the larger goal, making the overall process more robust and easier to manage. Immutability of decisions records. Where possible, treat important decisions or records as immutable. If a change is needed, create a new version rather than modifying the old one in place. This provides an audit trail, reduces confusion, and allows for easier undo capabilities. For instance, when collaborating on documents, tracking changes and versions is functionally superior to directly overwriting. Seeking predictability. In any system or process, strive for predictability. When an action is taken, its outcome should be consistent and easily understood, minimizing surprises. The journey continues. Learning functional programming isn't just about adding a new language or technique to your toolkit. It's about gaining a more powerful lens through which to view and solve problems. It cultivates a disciplined approach to software construction that prioritizes clarity, correctness, and composability. It's important to remember that programming paradigms are not mutually exclusive. The future often involves a blend of approaches. The best engineers will be those who understand the strengths and weaknesses of different paradigms and can fluidly apply the right tools and mindsets for the job at hand. By embracing functional thinking, you're not abandoning other paradigms. You're simply adding incredibly powerful principles that will make you a more versatile, effective, and insightful problem solver. As you continue your journey in the ever-evolving world of technology, keep these functional principles in mind. They will serve you well, guiding you towards building more elegant, robust, and understandable systems, both in code and in life. The way of functions is a path towards greater clarity, and the future is embracing it.